Hey everyone, I'm excited to talk to you about the physics of inclines, also called ramps. So you might be wondering, why are we talking about ramps? Well, two things. One, from a physics perspective, they provide really interesting, difficult, fun to solve problems. And two, we are surrounded by inclined surfaces. Up until this point, we've only been looking at problems that involve flat surfaces. But since surfaces that are at an angle are so common in our everyday life, I felt like it was important that we talk about it in physics class. So when we're looking at a problem involving an incline or involving a ramp, we're going to be looking at something that is on a surface that is tilted. And when we're doing these kind of problems, we really need to know how steep that surface is. And the way that information is going to be presented to us is in terms of an angle above the horizontal. So in this diagram, we are given the angle as theta. That's the Greek letter that you see here, theta. We don't always have to use the Greek letter theta, but more often than not, we're going to be given the angle above the horizontal as a Greek letter theta. So here we're looking at something that looks to be about 20 or 30 degrees just by an eyeball. And so let's say that the box that's shown in this diagram, let's say that it's stationary. So the forces on it have to be balanced in order for it to maintain its constant velocity of 0. What forces do you think are acting on the box? Hopefully one of the forces that came immediately to your mind when I said that was the force gravity pointing straight down. So that's one that we can always fill in right off the start. Another force, we know the forces in the vertical direction have to be balanced, and the surface is pushing on the box. So there's also going to be a normal force, which is going to be up and to the left. We know that it's up and to the left because normal force is always perpendicular to the surface. My surface is up and to the right. So if the surface was pushing on the box, that push would be up and to the left. Now you'll notice in the horizontal direction, the forces are now unbalanced because we're also missing the force friction, which is up and to the right, stopping the box from moving, sliding down the ramp. We know the force friction is up and to the right because force friction is always parallel to the surface acting because force friction is caused by the rubbing together of the two surfaces. So we can look at the horizontal direction and see that force normal is pushing to the left, and force friction is pulling to the right. So in the horizontal direction, they should be balanced. And in the vertical direction, the force normal plus the force friction pushing up are going to balance out with the force gravity pulling down. And if the box were to be accelerating either up the ramp or more likely down the ramp, in that situation, the forces would not be balanced. Specifically, if friction were to disappear, we would get more force to the left and more force down, so the box would accelerate down and to the left. So hopefully that makes a little bit of sense. But when we actually get down to solving these problems, we run into a tiny little issue in that if we keep our X, Y, horizontal, vertical coordinate axis system, you can notice that only one of these three forces is entirely in the horizontal or vertical direction. Only force gravity is going straight down. Both force friction and force normal have a component that is to the right or to the left and a component that is up. So if we were to try to solve this problem, we would have to break both of them into their horizontal and vertical components, which is totally possible, totally doable. It's just kind of a pain. So instead of doing that, we've come up with a creative workaround in that we don't have to stick with the horizontal vertical coordinate axis system. What we could do instead is just turn our heads a little bit to the side and create a new coordinate axis system. But instead of calling that the XY coordinate axis system, which might get confusing with the coordinate axis system I was just talking about, we give it a different name. We're going to call it the parallel and perpendicular coordinate axis system. So you'll notice the line that appears to be going in the X direction is parallel to the surface. And the line that's going up the page, because we kind of turned our heads a little bit, is going in the perpendicular direction, perpendicular to the surface. Now, this is really useful because it allows two of our three forces, we don't need to rearrange at all. The force friction is entirely in the parallel direction, and the force normal is entirely in the perpendicular direction. So the only thing we have to do is rewrite the force gravity into its parallel and its perpendicular components, and then the problems become much easier to solve. And I'll show you how to do that in just a minute. But here's what it looks like. If we take our force gravity and split it into its parallel and perpendicular components, we would get something that looks like this. Now, really important, I want you to write this down to know here, is that just like we were looking at the horizontal direction and the vertical direction differently, Here we can look at the parallel direction and the perpendicular direction. So the forces might be balanced in the perpendicular direction, but unbalanced in the parallel direction. Actually, most commonly, that's what's going to happen is because when something's sliding down a ramp in the perpendicular direction, it's not going into or away from the ramp. It's just sliding down the ramp. So often we'll see the forces as balanced in the perpendicular direction, but unbalanced in the parallel direction, either because it's sliding down the ramp and speeding up, or sliding up the ramp and slowing down. So just we can look at the two directions separately. Whoa, that was a blast. Anyway, let's do a practice problem together just to see. It's a little bit complicated, and I want to go through the first one step by step with you. Okay, so if we have a 5 kilogram box and it's sliding down an inclined plane at a constant velocity, that's a key word for the forces need to be balanced. Let's say the plane is elevated at 20 degrees above the horizontal, and the question is asking for what is the coefficient of friction between the box and the plane. So this also is a problem that involves a friction example as well. So the first thing I think we should do with all of these problems is just sketch a nice little picture. We have a theta, an angle of 20 degrees, and we have a box that has a mass of 5 kilograms. On top of that, we can start to draw our forces. We know we have force gravity, force friction, and force normal. And because the box is moving with a constant velocity, we know that in all the directions, whether it's vertical, horizontal, perpendicular, parallel, all the directions, the forces have to be balanced. So doing that thing where I break the force gravity into its parallel and perpendicular component, I have here drawn the perpendicular component and the parallel component. And you'll notice why I've drawn the parallel component so far down there in just a minute, because really we should move it up and draw it right next to the box, but I've drawn it down there for a particular reason, because in order to actually do the trigonometry to solve for the force gravity and break it into its parallel and perpendicular components, I need to know one of the angles inside the triangle that I've just made right there. Does everyone see how I made a triangle where force gravity is down, and then it has two legs, the parallel and perpendicular components of that triangle? And obviously a line that's parallel and a line that's perpendicular are going to make a right angle. So I've drawn in a right angle right there in my little purple triangle. And I've also drawn in a right angle in the bigger triangle that you see to the left. And the right angle that I've drawn in the bigger triangle is actually going to help us find an angle within the smaller triangle. So because we know that in the big triangle, all the angles have to add up to 180 degrees, we have a 20, we have a 90, we can go ahead and plop a 70 degrees right in the top right of my triangle. And then because we see that the horizontal surface makes an angle of 180 degrees and that there's a right angle right there, now I've done all this to get an angle inside my triangle, which is 20 degrees. So I've done that. So I can come up with the following two equations. The sine of that 20 degrees is going to tell me, because sine is opposite divided by hypotenuse, it's going to tell me the parallel component of my force gravity divided by the force gravity. And cosine is going to be equal to the perpendicular component divided by force gravity. Or if we want to write that another way, we could say because force gravity is equal to mass times the acceleration due to gravity, or negative 10 times the mass, we could say that it's mg, where g is negative 10, times the sine of theta. And then the sine of theta is going to give me the parallel component, and the cosine of theta is going to give me the perpendicular component. So we can use that information to actually then solve for the force gravity parallel and the force gravity perpendicular. So because we know the forces are balanced, we can go ahead and add in our equality marks. And again, you'll notice that in the horizontal direction, the forces are balanced, and the vertical direction the forces are balanced. And I had to catch myself just then because I said horizontal and vertical, but what I really meant was parallel and perpendicular. So in the parallel direction, the forces are balanced. In the perpendicular direction, the forces are balanced. Using the equations that we got from the last slide, we can substitute force gravity parallel, force gravity perpendicular for mg sine theta and mg cosine theta respectively, where mass times the acceleration due to gravity is our little g. And then we have to remember all the way back to the beginning of the problem, we were asked to solve for the coefficient of kinetic friction. So using the force friction equation, which is force friction is equal to the coefficient of friction times the normal force, we can rearrange to solve for the coefficient of kinetic friction, which is the force friction divided by the force normal. We can see in our force diagram that force friction is equal in magnitude to mg times sine theta, because those two forces are balanced, and force normal is equal to mg times cosine theta, because those two forces are balanced. So if we rewrite mg sine theta divided by mg cosine theta, you can see that the mg's should cancel out, and sine divided by cosine we know is tangent. So actually it all boils down to just one really simple thing. The coefficient of friction is going to be equal to the tangent of the angle that we were given. Since we were given an angle of 20 degrees, we're going to get a coefficient of friction of 0.36. Now, let's stop and check our answer just to make sure that it all makes sense. First, let's check the units. That's going to be newtons divided by newtons, so it's unitless. So that's good. And then on top of that, most coefficients of friction are some number between 0 and 1. You can get greater than 1 if you have like a really, really, really sticky surface, but the fact that this number is 0.36 is right in kind of the acceptable range for coefficients of friction. So that was an example problem involving ramps. I know it was a lot. These are like the hardest problems that we've done up until this point. So make sure to go back and rewatch if you need to, and then try a couple of the problems for yourself, which we'll talk about in our next class.